Thank you very much, and thank you for coming. So this is going to be a talk about certain classes of partial differential equations. So I'm sorry for you, but at least from somewhere I have to start, and I have to start from partial differential equations. So one of the main players in the talk is the so-called incompressible Euler equations. So they are, it's a very old system of partial differential equations, which was effectively derived by Euler more than 250 years ago. It's one of these rare occasions in which the system is attributed really to apparently the first person who wrote it down in the mathematical literature. So it's a system of partial differential equations for the velocity and the pressure of any incompressible fluid. So I will write it in the following way. So u is the velocity of the fluid. So it gives you, as a function of the point x and the time t, the velocity of the fluid particle, which at time t is actually sitting at the point x. It's a little bit less intuitive what this pressure p over here is. So you see that I have the divergence-free constraint. So this is telling you that the amount of fluid which is occupying a certain region is always constant as a function of time. So this means that if fluid particles want to go into kind of the same place, there is an obstruction to do this. And you can think about this pressure as a reaction to the willingness of the fluid to actually kind of compress something. Okay, so P is a scalar. So U and P is therefore a pair which is going from some domain omega times I, where I is an interval of time and omega is a subset of, say, the three-dimensional space, for instance, or it could be the two-dimensional space, and this is going to R3 times R. Okay, so as I already said, physically this law here, this conservation law here, says that if I take a fluid element, so if I take a region of space, say U, so for every region of space, which is sufficiently smooth, what I have is that the amount of fluid particles which are leaving actually this space is equal to the amount of fluid particles which are entering this space. Okay, so you can actually express, therefore, this law over there, the divergence of u equal to 0, with the following balance law. So if I integrate over the boundary of my fluid element, u times the normal to the fluid element, this is always equal to 0, which is telling you that during the time there's as much fluid staying in u as at time 0. So here's my region u, which is inside omega, and nu is actually the outward unit normal. You can write something similar for the first equation. So the first equation is the balance law of momentum. And if you're wondering what happens to the amount of fluid which is sitting in this region u, you can actually, from that equation, from the first equation over there, you can derive that the time derivative of the integral over u of your velocity u, so this would be the momentum. So this is equal, or somehow if I sum this, so I guess I have to actually change the sign. So this is equal to the integral over the boundary of u dot nu. So this is a term, and then there is p times nu. Okay, so this is telling you that the momentum is actually changing because maybe there are some fluid particles which are flowing in and out, and they carry their own momentum. So this is what is happening. And then there is actually a force which is exerted by the surrounding fluid, and which is proportional to the pressure, and it's orthogonal, right, to the configuration. I mean, to the boundary of u. You also see that. I mean, you might wonder, because this pressure p is defined up to a constant, but you see that if here the pressure p is a constant and I'm integrating over the boundary of u the unit normal, then I get 0, right? So you see even from this equation that there is this kind of degree of freedom. Okay, so why actually did I write these things here in this way?
Did u tensor u?
Oh, yeah. So very good question. So I just mean that I'm summing over I the spatial derivatives of ui, uj. So I take the components. So these are the components somehow of the matrix U tensor U. And I'm taking the divergence of each line. And since the matrix is symmetric, if you want to take the divergence of each row, somehow it's fine anyway. I always pick up the wrong convention. I think it's actually correct to take the divergence of each line. And you might also observe, and this is the way usually actually the equations are written down, if U is actually a smooth vector field, and I'm assuming that the divergence of U is equal to 0, so when the derivative eats ui, I don't get anything, right? I get 0. So this is the same as writing the sum over I of ui di uj. Okay, and this is usually how actually the equation is written in the literature, in physics and engineering literature. But I prefer to write it down in that way because then it becomes apparent that I got, for instance, this by integrating divergence of U tensor U by parts, right? Which otherwise wouldn't be that obvious. So why did I actually write this down, right? Because it seems like a derivation which I'm giving you from the actual equation. Well, usually in textbooks it's actually the other way around, right? So in textbooks you start postulating that your fluid is incompressible, which is the content of this equation over here, and you start postulating that there is no that if region of fluids are sliding over each other, there is no friction between them. So there is no loss in the total momentum because of some friction between the particles. And then you derive this equation over here. And if you now do the opposite direction, so if you integrate this by parts and this by parts, you then derive that the integrals of those quantities have to be equal to 0 for every reasonable fluid element, which, of course, in turn, it tells you that the U and P have to satisfy that system of partial differential equations. Okay? On the other hand, so there is something which you can do, and this is done both in the physics literature and in the mathematics literature. You can actually postulate that you don't have enough differentiability for the functions to derive the PDEs over there. And you might take this balance law for every fluid element as a good definition of a solution which is maybe rough. Okay? So from now on, when we are talking about a weak solution of the incompressible Euler equations, so this is a pair, UP, which we might take to be continuous functions. Such that these two balance laws, say A and B, are satisfied for every smooth regions U inside omega. Okay? So there is yet a third interesting physical balance law for these fluids. So since actually there is no action of a force on the fluid, you're expecting that the fluid conserves the energy. And in fact, if you are in a sample omega and you put some rather natural boundary conditions, for instance, the fact that the fluid is not escaping your region omega, which would mean that in your region omega, which is kind of containing the whole universe, so here the fluid is actually tangential, so the velocity of the fluid is tangential to your domain in such a way that nothing is actually exiting and nothing is entering. Then if you have a smooth solution, so if UP is C1 and U is orthogonal to the normal nu at the boundary of omega, then it's not so difficult to show that the time derivative of the integral of modulus of U squared divided by 2, which would be the total kinetic energy of the fluid, is actually equal to 0. Okay, and if you want, you can write down actually what happens in general. In general, it would happen that this thing over here is equal to the integral of U dot nu, and here you will have modulus of U squared divided by 2 plus P. Okay, so this U dot nu is equal to 0 at the boundary means that this thing sort of disappears. Okay, and this is nothing surprising. It's just the law of conservation of the kinetic energy. Okay, so it comes therefore as a surprise if you open the physics literature and you discover that in a very well-known paper in 1949 by Lars Onsager, Nobel Prize in chemistry and one of the most prominent theoretical physicists of the 20th century. So he actually conjectures that in general weak solutions of the Euler equations in this sense do not preserve kinetic energy. Okay, so he conjectures the following. So if U is in C0 alpha, so it's Hoelder continuous with alpha less than 1 over 3, bigger than 1 over 3, then U is energy preserving. And if U, so there exists U, which are in C0 alpha for every alpha less than 1/3, or maybe I should actually do it the other way around. So for every alpha less than 1 over 3, there exists actually solutions with this Hoelder continuity such that, or which are energy dissipative. Okay, so let me just tell you the two things more. So what do I mean by Hoelder continuous? I actually mean Hoelder continuous in space. So it means that for every point x and y, U is satisfying the following inequality with the constant c, which is independent of time and the 2 points x and y. So this is for me alpha Hoelder, or where I write that U belongs to C0 alpha. And actually, to tell you the truth, Onsager is not considering a fluid which is living in some fluid sample omega, as I actually post over here. But to avoid issues with the boundary conditions, it's actually assuming that omega is the periodic torus. Okay, then it's bounded. I can integrate my function and get some, I mean, my modulus of U squared and get something finite, and I don't have to worry about boundary conditions. And in fact, here, omega is just the 3-dimensional periodic torus. Okay, so how it comes actually that back in 1949 is making this conjecture, and often, at least if I am in the audience and I'm listening to a mathematician talking about something that the physicist said, I'm always very kind of skeptical, because usually physicists are saying something and then the mathematicians translate it into something else, or the other way around. So it's in fact remarkably exactly the way I stated it. So he's not considering, okay, so he does not define weak solution in that way, which is kind of, which I did because it's kind of nice, but he defines weak solutions precisely in a slightly different way. So what he actually does is the following. So the definition of weak solution for Onsager is the following. So he writes down U of xt in Fourier because he's on the periodic torus. Okay, then he writes down the smooth systems of partial differential equation as an infinite dimensional system of ODEs for the Fourier coefficients. And then he just notices that when you write down each equation, okay, so to give meaning to the right-hand side, you need these coefficients to be square summable. So as long as you are actually in L2 and you write down your infinite system of ordinary differential equations, you can make sense of this. And now, energy dissipative, what it means? Well, of course, I think for a physicist, this is kind of acceptable, maybe borderline acceptable to have a fluid which is dissipating energy, although it shouldn't do. But to have a fluid which is actually increasing energy is obviously not acceptable. So by this, we just mean that the time derivatives of this guy is strictly less than 0. Okay, but strictly less. So somewhere it's really going down. Now, there's, however, a caveat over here. There is a change. There is a coordinate transformation which preserves the Euler equations and changes time in minus time. So strictly from the mathematical point of view, unless I tell you that for some reason you don't want solutions with increasing kinetic energy. As soon as I have solutions with decreasing kinetic energy, I can just make the change of variable and find a solution with increasing kinetic energy. Okay? Very good. So why is actually advancing these conjectures? So there are so.
What is the law of the pressure? What is the constraint on the pressure?
Nothing.
No.
Right. No. Yes. Okay. So maybe something that I should point out, if you write, so you can always eliminate the pressure from your system of partial differential equations in a way by solving an elliptic partial differential equation. So I could actually, I could formulate the equation only on U. And in particular, if, for instance, you take this point of view in which you have an infinite system of ordinary differential equations, okay, at first you derive an infinite system of ODEs where also the Fourier coefficients of the pressure are involved, but then you can actually eliminate them and write down a system of, an infinite system of ODEs in which only these guys are entering.
But this doesn't constrain the time derivative of the pressure in any way.
Yeah, it doesn't, right? Okay, so the pressure, on the other hand, there's an equation which, once you know the velocity, there's an equation which is determining the pressure. The pressure is not determined up to a function of time, which is, however, constant in space. But see, we write it as gradient of P, but what really is physical, P is not that meaningful. It's really the gradient of P which is meaningful. So if you insist on the gradient of P is actually uniquely determined once you know U. So then finally, the gradient of P is really constrained. If you want, I just can ask that the average of P along the time is equal to 0. The average of P in space is constantly equal to 0, and then the pressure would be uniquely determined by U. And that's maybe also the reason why you kind of don't see it over here. Anyway, once you have that U is Hoelder continuous, the pressure will be Hoelder continuous also with some modulus. So good. So there are two things which are strongly linked with this conjecture. So what is the motivation for the conjecture? So there are two key facts in the theory of fully developed turbulence. So one, which is the thing from which he was starting, is that if instead of considering the Euler equations, I consider the Navier-Stokes equation, in which I have a dissipative part, which is usually epsilon the Laplacian of U. So the Laplacian is, as usual, the sum of the second-order mixed derivatives, and this epsilon is a positive parameter. Okay, if I am on a periodic torus, I can write actually the corresponding identity, and then I would have, if I have a smooth solution, I would have that this integral. Of course, this is this time not preserved because I have a dissipative term which is penalizing layers of fluids sliding on top of each other. So there is some friction which is modeled by this epsilon Laplacian of U. So this is equal to minus epsilon times the integral of the U squared of x t dx. Okay, so if you let epsilon go to 0, and this thing is converging to a smooth solution of the Euler equation, of course, this right-hand side would actually converge to 0. That's what you would expect. On the other hand, it's one of the main assumptions of the theory of fully developed turbulence, which was started by Kolmogorov in 1941, that in fact, this quantity is, for most solutions of the Navier-Stokes equation, or if you want statistically for almost all solutions, is actually independent of epsilon. So although you have epsilon going to 0, you should be able to find plenty of solutions for which this quantity stays bounded away from 0. If you accept this, then the step of Onsager is just to say, okay, so let epsilon actually go to 0, and maybe I can postulate the existence of solutions to the Euler equations which are not preserving the kinetic energy, okay? Because it leads naturally to this. This exponent 1/3 is not something which comes somehow out of the blue. So actually, it's another law of the theory of turbulence that you can find on textbooks, that if you look at, I mean, if you think that you're looking at random solutions of your Navier-Stokes equations, where, I mean, random has to be defined, and as far as I know, it's not yet actually defined in a sense which is acceptable for mathematicians. But I mean, if you look at a random sample of fluids, what you expect or what you observe is that the expectation of the difference in the velocity between 2 points which are separated by a distance delta x actually behaves like the distance delta x to the power 2/3. Okay? So here you have the power 2, here you have the power 2, and then you have this exponent 1/3. Okay. So it's like as if you would expect that statistically solutions have to be Hoelder continuous with an exponent 1/3. Okay, so now part A of the conjecture is a theorem. And this was proved by Konstantin A. and Titi in 1994. After a previous work by Eying around the same time, which didn't quite prove A, but proved A in a scale of spaces which is not exactly the Hoelder spaces. So a scale of spaces which has 1/3 of a derivative, because you can imagine that this alpha here is just telling you how much derivative the function has in a certain sense. So Eying was actually able to prove this for a scale of spaces which has 1/3, I mean a little bit more than 1/3 of a derivative, but which is definitely stronger than these Hoelder spaces. Okay, I don't want to go into the detail. Okay, and theorem B is also, so B is also a theorem. So B holds as well. Okay, and this was the end of the story 1 or 2 years ago that I started with my friend Laszlo Zekai-Hidi in a series of papers. And then there were very important contributions by several people, Buchmaster, Daneri, and Laszlo. And then a paper which was fundamental and finally reached actually this threshold exponent 1/3, which is by Phil Izet. Okay, so Phil Izet actually proved in effect that for every alpha less than 1/3, there is a solution which is not preserving the kinetic energy, so for which somehow this quantity over here is not constant. But his solution does not have dissipative energy, so this was improved by Tristan, myself, Laszlo, and Vlad Vikol last year. So this really gives you just dissipative. Okay, but let's say it's a second. It's a second order correction, right? So the main result achieving the borderline exponent here, alpha equal to 1/3, is due to Phil Izet. And what happened in between is that in these papers with Laszlo, we construct first a solution which was continuous and was dissipating the kinetic energy. Then we had works having the first Hoelder exponent, which is 1/10. Then the Hoelder exponent went up to a certain point. So together with Tristan Buchmaster, we had a solution which had 1/3 of a derivative, but was not in this scale of spaces. So it's a little bit like Eying result from this point of view. And then finally, Phil was able to actually get the correct result over here. Very good. So now, why did I call though the talk threshold Hoelder exponents? Okay, because so first of all, the first theorem which was out there and which showed the existence of solutions for which the energy was not conserved is in a paper in 1993 by Vladimir Scheffer, and he actually proved that there exists L2 weak solutions which are compactly supported in space and time. Okay, I mean, stated in this way, there's obviously one compactly supported solution in space and time, which is the zero solution. So here I just have to add non-trivial. Okay, so this is a solution which at a certain negative time is identically equal to 0, then has positive energy, and then has identically equal to 0 energy again. Okay, so obviously the energy is not conserved because it's increasing somewhere and then going down somewhere else. Okay, so this was actually a rather complicated proof, and where the story started, it started with a theorem by Laszlo and myself way before actually we approached this conjecture. So this is in 2007. And we could give a proof of Scheffer's theorem, but actually even an improvement of Scheffer's theorem, in which you see that we're going into the direction of continuity. So there exists L infinity weak solutions compactly supported in space and time, but even more. And now I'm going to explain you what I mean by the more. Now, in between this, there was a different proof by Sascha Schnirelmann. So there were two rather important papers by Sascha Schnirelmann in 1998 and in 2000. In 2000, he was able to produce a solution which has energy which is going down. But I want to tell you a little bit about the more. So the more is that we identified an interesting mechanism leading to these theorems over there. And the interesting mechanism is the following. So just for the moment, step back and make the following remark. So assume I give you a sequence UK. So this is a sequence of solutions of the Euler equations. And even assume actually that this sequence of solution is smooth. Okay, but I don't tell you anything more about these solutions. Then, of course, the energy, I mean, they're smooth solution. You can derive the energy identity. And what you know is that the energy at any given time is equal to the energy at the initial time. Say, this would be for some initial time k0. Okay, so now assume at the initial time I give you a uniform bound. So I tell you this is bounded away from past infinity independent of k. Then you have a uniform L2 bound for your solution. And in 3 dimensions, this seems to be the only information which is available. I mean, you have other conserved quantities that you can write down from physical considerations, but they don't seem to give you any control, any other kind of bound which you can effectively use to control what is happening to the limit. So now once you have a uniform control on the L2 norm, of course, you can extract a subsequence which is converging weakly to some u. But obviously, once you actually get something which is a weak solution, I mean, once you have actually weak convergence, if you cannot upgrade this convergence to something better, you, of course, don't know that the limit of UK tensor UK is U tensor U. Okay, because taking products does not commute with weak limits. So although you have an equation for this UK, you're not able to derive an equation for U tensor U. Okay? So never mind. So assume I kind of forget about this thing. And I say, well, OK, UK tensor UK is not converging weakly to U tensor U. But let's say it's converging to some U tensor U plus whatever, some error term R. Actually, let me put this error term in this way, minus R. OK, then you have a solution to the following forced Euler equation. So you have an error term. And this error term is not arbitrary, you can actually derive some bounds for this error term, which is coming from the fact that the total energy over here is less or equal than constant C. I mean, things could go so wrong that, I don't know, U tensor U is, for instance, equal to 0, and then all that is happening is that this R is actually remembering that you come from a weak limit of something which does not have energy, which is going to 0, okay? But you get a bound on R, okay? So let me give you a cartoon picture of another partial differential equation, for which you could think something similar is happening. So say that I give you a solution of the following partial differential equation. Say modulus of gradient of uk is identically equal to 1. Okay? So if you were, let us maybe give a different name, wk. So if you were in 1D, right, this would mean that the function has slope 1 or maybe minus 1. Okay? If I give you a sequence of functions who are Lipschitz on 1D and they have slope 1 and minus 1, right, if I don't know anything else, of course they can make a lot of zigzags. Okay? So they would have a uniform Lipschitz control. I mean, they would have a uniform control on the Lipschitz constant. So they're obviously converging uniformly to something, but they might converge uniformly to something which has slope strictly less than 1. Okay? And in fact, you can make the following exercise. Take a function which has slope less than 1. So this function has like modulus of w prime strictly less than 1. It's not difficult to see in one dimension that you can approximate it as well as you want. Probably not as I'm doing somehow in this picture, right? Because that one is not even a function. Okay, so you can approximate it as well as you want, right, by solution of your partial differential equation. Okay? So of course this is not surprising. It's just telling you that the iconal equation is kind of soft. Okay? Apart from telling you that the slope has to be either 1 or minus 1, is not telling you anything more. Okay? Of course, you could insist on having special solution of the iconal equation. One special solution would be kind of the maximal one, right? So the one which reaches the maximal height. And then you lose the softness. But if you don't impose anything else, you have this softness, and you can show that actually any solution of the relaxed problem can be approximated by an exact solution. Now, here there's something similar. And what actually our theorem over here says is that a very similar principle to that of the iconal equation exists. So take a solution to the relaxed problem where the only constraints that you put on R is what comes naturally out of this convergence, which is just essentially a Jensen's inequality or a convexity inequality, which is the very same convexity inequality which is telling you that if I am a sequence of solutions with slopes 1 and minus 1, it converges to some function that has slope in between. Okay? And I will be able to approximate, in a suitable sense, any solution of that relaxed problem with a solution of the Euler equation. Okay? So this comes with an extra statement, which we call an H principle. The person who can actually challenge this is somewhere else today. So the H principle, which is telling you, so any solution of the relaxed problem can be approximated by exact solutions. Okay, and this is very surprising because it's telling you something which is unexpected, at least was unexpected. That is that, at least at the level of weak solutions, the solutions of the Euler equations are rather flexible. So you would expect that there is some rigidity. For instance, you would expect, I don't know, they are unique because it's a system in classical physics which is determined. But if you're just looking at weak solutions, then it's actually rather flexible. So this was in L infinity. Obviously, there is a big step between L infinity and continuous, big step between continuous and Hoelder. So how did we actually come with the idea that you could possibly approach the Onsager conjecture from this point of view? Okay, so there was a very similar, so there was not a very similar, but there was an analogy which was drawn back in 1999 by Müller and Schwerak, So Müller and Schwerak gave a construction of some terrible solution of a system of partial differential equations, which is elliptic, but that is not interesting for us. So what they actually pointed out is that the mechanisms, so some mechanisms in PDEs used in the theory of differential inclusions, and the diagonal equation is a primary example of a differential inclusion. Had or have lots of analogies with results somehow classified as H principal or as H principles in differential geometry. Okay, and let me give you kind of the mother of all these results, which is called Nash-Kuiper theorem. And so let me switch to differential geometry. So we consider here isometric embeddings of Riemannian manifolds. So say you have a Riemannian manifold sigma g. U from sigma to g, from sigma to Rn is an isometric embedding if it preserves the length of curves. Okay, so if G is a smooth metric, well, even a continuous metric, and U is actually a C1 embedding or immersion, this is just equivalent to a system of partial differential equations, which in coordinates you can simply write as diu scalar product with dju is equal to gij. Okay? And the theorem that Nash and Kuiper actually proved over here is the following. So if, say, V from sigma to Rn is a short, curve shortening immersion, respectively embedding, then V, and the dimension of n, the dimension of the ambient space is strictly bigger than the dimension of sigma. Then V can be uniformly approximated with isometric immersions, respectively embeddings. Okay? So there's a very similar principle over here. If I give you a sequence of curves of a certain length, right? So of course these curves, they are converging to a limiting curve, but the limiting curve can actually have strictly shorter length than what you started with. Okay, so I can take just something like this and start making a lot of zigzags. So something very similar happens over here if I don't tell you anything more, and I have a sequence of isometric embeddings or immersions. These are somehow a sequence of maps which preserve the length of curves. What might actually happen in the limit is that the limiting map, which exists because of Ascoli-Arzelà, because you have uniform Lipschitz control on the isometries. So this last one can actually possibly shrink the length of curves. Okay. Nonetheless, it's very surprising that it does it in such a dramatic way. So you have to contrast this theorem which applies for two-dimensional surfaces in R3 to the following classical fact. So if sigma g is positively curved in 2D, and C2 and U is a C2 isometry or isometric immersion, then U of sigma is locally convex. Okay? So in particular, if I apply the Nash-Kuiper theorem, I take a sphere of radius 1, a standard sphere of radius 1. I make a curve shortening map, which is taking this sphere into a sphere of radius epsilon. Then the theorem is telling you that I can uniformly approximate the sphere of radius epsilon with actually immersion. Okay? So which must have a lot of wrinkles just to fit everything in a ball of radius 2 epsilon. But if I actually look at C2 isometric immersions, C2 isometric immersions of the round sphere have to be a convex body. A convex body of total area equal 4 pi. And I can't possibly squash it into a very small ball. Okay? I might try to elongate a convex body, but not squash it. In fact, at this level, if sigma is a two-dimensional sphere and it's 2D and positively curved, then there is a classical theorem by Herglotz and Convossen, which tells you that the isometric immersion is uniquely determined up to rigid motions. Okay? So it's even more severe than just saying that it's convex. So you kind of see a striking difference between this theorem, in which the isometry is C1, and this theorem in which the isometry is C2. In a nutshell, what you could actually think is that when you are C2, you get a second fundamental form, which is well defined. And then Gauss' theorem is telling you that the determinant of the second fundamental form is equal to the Gauss curvature. With C1, you cannot possibly do that, right? So because it's actually the Gauss theorem which is telling you that since the determinant of the second fundamental form is equal to the Gauss curvature, then at each point your surface must be locally convex, okay? So if you believe us that we were saying Euler looks a little bit like differential inclusions, looks like iconal equation. And if you believe Müller and Schwerak, which are telling you, oh, they actually do look like this Nash-Kuiper theorem, or this sigma isometric embeddings business, then you see something interesting in the computations that I gave you for Euler, because I told you for Euler, if I have C1 solutions, the energy is conserved. So the PDE comes with an extra identity, which is not for free when you are C0 or L infinity. And the isometric embeddings come with an extra identity, which is Gauss theorem egregium, which for C1 would be false. Okay? So you see the same dichotomy. But not only you see the same dichotomy, so you also see something very interesting. So this is a theorem that Borisov proved in 1958. This classical fact holds for C1 alpha isometric embeddings with alpha bigger than 2/3. And then he announced in 1963, so the Nash-Kuiper theorem holds for C1 alpha if alpha is sufficiently small. This was actually an announcement. He only published much later a proof of a particular case which was not matching exactly the exponents that he was saying. But we have a paper with Sergio Conti in which more general results than this 1963 paper of Borisov are actually proved. So this was back in 2013, I believe. No, this was before. This must have been like 2010. Okay, so proofs. Now, of course, once you see this, you might be tempted to say, aha, so there's an analogy between the two problems. And in fact, what we exploited in this series of papers that we started back in 2012 to construct continuous solutions was similar idea to that of Nash and Kuiper in the context of the Euler equations. So not only actually we were able to kind of give sort of similar arguments in the case of the Euler equations, which apparently seem to bear no relations, but surprisingly, it has also been possible to nail down this optimal exponent alpha. Okay, so here for the isometric embedding problem, you can actually ask: is there a critical exponent which would kind of distinguish between these two behaviors, between kind of the rigidity type theorems and actually the flexibility type theorems that you have here below? Okay, and let me so therefore state a conjecture which up to now we don't yet know how to solve, and the conjecture would be the following. So if sigma g is 2D positively curved surface, then A for every u from sigma into R3 C1 alpha isometric immersion with alpha strictly bigger than 1/2, then u of sigma is locally convex. And B for every alpha less than 1/2, there exists u, okay, for every alpha less than 1/2, and say for every v sigma into R3 curve shortening map, curve shortening immersion, there exists u in C1 alpha isometric immersion arbitrarily close to V. Okay, and if I understand correctly, I think this is what Gromov conjectures. And if Borisov is not alive anymore, so if my information on people who discussed with Borisov, actually former colleagues of his, is correct, then Borisov actually believed this very same conjecture. So we are very far from it. Well, very far. This depends on how optimistic you want to be. So as I told you, what we know as a theorem, which was proved originally by Borisov, and then we had this shorter, this kind of other proof. And surprisingly, it's a much shorter proof, and it uses actually ideas from the Euler equations for the positive part of the Onsager conjecture. So what we know on A is that alpha bigger than 2/3 is okay. There are lots of reasons somehow to believe that this 1/2 is the correct threshold exponent. I could give you some intuitive explanation for this, or some results, some theorems that we can actually prove, but there's no time for that. So for B, the best that we can do is that if sigma is a disk, then B is true for every alpha less than 1/5. Okay, and this is a joint work of myself, PhD student of mine, Dominik Inauen, and Laszlo, back in 2015. And Laszlo and a postdoc of his So they have one paper and probably a forthcoming paper that should cover sigma being also a sphere. Okay. On the other hand, let me just tell you that maybe, or one thing which I believed for quite some time is that this conjecture is so hard, I mean, it's comparatively harder to the conjecture, the Onsager conjecture to prove because we are shooting to a very ambitious result. I mean, if you look back at what we were doing for the Onsager conjecture, we were saying, okay, so there are solutions, I mean, solutions above a certain threshold conserve the kinetic energy, and solutions below a certain threshold, they do not. What we are trying to do over here is something like solutions above a certain threshold, they're completely classified. I mean, they're convex, and then you can apply actually convex and ergots. And solution below, they're just completely wild. Okay? So Laszlo and I, for a certain period, thought, okay, the real kind of, the real analog of the Onsager conjecture should be something like if you have an isometric immersion, there is something extra which is coming to it, if it is sufficiently regular, something like the energy. So an extra PDE, if you want. And we should be able to say above a certain threshold, this extra PDE is correct. And below a certain threshold, this extra PDE is not correct. OK, so this we can do. So this is a theorem with Dominic Inauen that we just posted on the web. And let me tell you the exact statement, because it's rather cute, I would say. I mean, it's not the most general statement, but it's something which is very easy to explain geometrically. So this is a result with Dominic Inauen. OK, and let us just look at the following problem. So this is a problem which was already studied by Hoelder, Bühler, and Wasem back in 2013, I believe. And it is also studied in this paper by Kao and Laszlo in 2018. So, and the paper, I mean, and the problem is the following. So let's fix somehow a sigma with a certain boundary. And what I want to do is I want to take an isometric immersion U from sigma into Rn. But I want not only it to be an isometric immersion, but I also want to prescribe what U is doing at the boundary. So U at the boundary is prescribed. OK, then this was actually proved by Hoelder, Bühler, and Wasem in 2013. I mean, it's a kind of, Dirichlet problem, if you want. So I have a portion of the boundary. I'm assigning you the map over there. If you're just looking at C1 isometric immersions or embedding, you can do the same business that Nash and Kuiper did. OK? But now let me just make the following very simple remark. So let us look at even a subproblem. And the subproblem is the following. So assume your sigma is a polar cap. So sigma is a polar cap. OK, so if you want to put it in R3 as a polar cap, this would be simply x1 squared plus x2 squared plus x3 squared is equal to 1. And x3 is bigger or equal than some, say, 1 minus a. OK, and now let us look at isometric embeddings. And let us simply say U has to go from sigma into R3 or even Rn. So this has to be an isometric immersion or embedding. But U at the boundary of sigma has to be exactly this map. So has to be, say, x1, x2, and then for one coordinate has to be 1 minus a, and then let's say the others are all 0. OK? So now your boundary data is smooth. If you were looking at a smooth isometric embedding, you can compute the curvature of the curve in Rn. And then you can project this curvature vector on the tangent. And the projection of the curvature vector on the tangent would be the geodesic curvature of your boundary of sigma, right? So the geodesic curvature is actually prescribed, which tells you that the projection on this has to have a certain size, okay? In particular, you see that I cannot, for instance, hope to find a smooth isometric embedding if I impose the tangent at the boundary to just be too low, okay? So if I try to find a smooth isometric embedding and I try to actually go this way, then I will not be able to do it, okay? So, and now here's the theorem. So if you try to solve this problem in any codimension, and you have C1 1/2 plus epsilon, then the same constraint that you find for smooth solutions by using this geodesic curvature argument is correct for the C1 1/2 plus epsilon immersions. So theorem, let's say this would be part A for C1 1/2 plus epsilon isometric immersions. You could say geodesic curvature of the boundary of sigma equals the projection of the Euclidean curvature. And in particular, geometrically, this gives you a constraint on the angle with which you can start at the boundary. And then here is the theorem B. The ugly part is that I need a very large codimension, but in very large codimension, you find C1 1/2 plus minus epsilon isometric embeddings with horizontal tangent at the boundary. Okay, so in that picture over there, in very high codimension, you would be able to actually start this way at the boundary and then make an isometric embedding, which is kind of, okay, floating in these other dimensions and making something kind of crazy. Okay? Now, very large codimension means, unfortunately, 12, which is really not nice. Okay, so that's all I wanted to tell you. Thank you very much.